Okay, so we've defined what the partition function is and how we can use it to calculate probabilities. And to get a sense of this, how to use this thing, I'm going to focus on a simple example. So the example is going to be a classic example in statistical mechanics, which is a two-state system. So have two energy levels, 0 and epsilon. So it's a two-state, just those two states. A two-state system. And let's say you've got an atom which can move between these two levels. So it could have energy 0 or it could have energy epsilon and move back and forth between those two. And those are the only energy levels that it can have. So, and we want to think about what happens to this atom as the temperature changes. So hopefully it's not too hard to imagine that as T goes to 0, so a really small temperature, you would expect the probability that the atom is in state, let's call this one psi 1 and psi 2. The probability that the atom is in state psi 1 is equal to 1. And the probability that the atom is in state psi 2 is going to be 0 at very low temperature. That makes sense because if it's a very low temperature, it has no thermal energy to jump up to the higher energy state, right? So now I want to kind of have you think about it a little bit. What do you think is going to happen as T goes to infinity? What do you expect the probability that the atom is in psi 2 to be? So here are some choices. How about 0, 1/2, 1, and something else? So we talked about the low temperature limit here. We kind of expect it to always live down in that ground state with zero energy. And what about a high temperature? What do you think that the probability it's going to be up there is? Go ahead and pause the video, see if you can answer based on your intuition, and then we'll work out the system together. So I asked you to predict what's going to happen as T goes to infinity at very large temperature. What's going to happen to this atom in these two-state systems? So let's work it out. So first thing we're going to do, let's calculate Z. It's the sum over all states. And then for every state, you take e to the minus the energy of that state divided by kBT. Okay, so in this case, there's only two states. So there's only two terms in the sum. It's going to be e to the minus E1 over kBT plus e to the minus E2 over kBT. Okay, and E1 is 0. So there's 0 energy in that state. And E2 is epsilon, minus epsilon over kBT. So that means that Z is 1 plus e to the minus epsilon over kBT for this two-state system. Now let's think about what's the probability that I'm in each of those states. So the probability that I'm in psi 1 is e to the minus E1. So now I'm using this formula here. Sorry, I'm not using that formula. I'm using this formula. They're the same formula because there's no degeneracy in this case, but that's what I'm using. E to the minus E1 over kBT divided by Z, which is 1 plus e to the minus epsilon over kBT. But E1 is 0, so that's e to the 0 over, let me just save myself some writing. So that's going to be 1 over 1 plus e to the minus epsilon over kBT. Okay, that's the probability that it's in state psi 1. What's the probability that it's in state psi 2? Very similar. Very similar, except E2 is epsilon. You can check, if you want, check that the probabilities add to 1. P of psi 1 plus P of psi 2 is equal to 1. It's not too hard to see that that's going to work because this 1 plus this is going to be equal to the denominator, so it'll end up being 1. So there's my formulas for the probability. Okay. Now let's think about what do these mean. Let's do that on the next slide. So let's check to see if these formulas make sense. So let's do some physical checks. There's really only one physical check. We're going to check the low temperature limit. What happens if I send T to 0? What do I get? P of psi 1 is going to be 1 over 1 plus e to the minus epsilon over 0. But 1 over 0 is infinity, so that's 1 over 1 plus e to the minus infinity. And e to the minus infinity is 0, so that's 1. And P of psi 2 is equal to 1 over 1 plus, not 1. So the numerator is e to the minus epsilon over 0. 1 plus e to the minus epsilon over 0. So that's e to the minus infinity over 1 plus e to the minus infinity, which is 0. Okay? And that agrees with what we thought before, that at very low temperature, the atom's going to spend basically all its time in that lower state. Okay. Now, what did you think is going to happen at t goes to infinity? Let's look at this example. T going to infinity, what happens? P of psi 1 is 1 over 1 plus e to the minus epsilon over infinity. But e to the 1 over infinity, that's e to the 0. So 1 over 1 plus e to the 0, which is 1 over 1 plus 1, which is a half. And you can similarly show the same thing happens for the other one. Okay, and so the probabilities add to 1. So I don't know, maybe you predicted this, but I certainly didn't the first time I saw it. I certainly thought that when temperature went to infinity that this atom would spend all of its time in the higher state. But in fact, it spends its time equally 50-50 in the lower state and the higher state. And the reason for that is that basically when you have so much available thermal energy, that what happens is that there's no barrier for that atom to go up to the higher state. It can do it very easily. There's no cost to it. There's so much abundant thermal energy that it can easily go to the higher state with it. It just feels like nothing. And now you're back to kind of like being in a box where it could be on the left side or the right side, and it doesn't cost anything to be on the left side or the right side. So it will spend its time equally. It's equally likely to be in the lower state and the upper state. So that's one really surprising result that comes out of these Boltzmann statistics or Boltzmann distribution for the two-state system. So the last thing I want to discuss before we move on from this example is the average energy of the atom. Let's call the E bar, right? Bar means average. So what's the average energy of this atom? How do you calculate an average of something? So average of x. So x is some quantity. It's just some, could be anything. How do I calculate it? I calculate it by adding up all the possible values that x could take. So xi is the value that x could be. But then it's a weighted average, right? If they're not all equally likely, I have to multiply by the probability of getting xi. So xi is the value x could take. And then p is the probability with which that occurs. So let's do the example with the energy. What's the average energy in the two-state system? Well, it's I have to add up all the possible values of the energy EI times the probability at which those energies occur. So in this case, there's only two states. going to be E1 times the probability of finding the atom with energy E1 plus E2 times the probability that the atom has energy E2. Okay, E1 is 0. So this is 0. Because this is E1, right? E1 and E2. E2 is epsilon. So that means that the average energy of this system, the first term is 0, is epsilon times P of E2, which is this guy here. So it's going to be epsilon times e to the minus epsilon over kBt, 1 plus e to the minus epsilon over kBt. You can make this look a little bit nicer if you multiply the top and the bottom by e to the epsilon over kBt. And then the top just becomes epsilon, and the bottom becomes 1 plus e to the epsilon over kBt. Okay, so there's the average energy of this system. And you can again check what happens in those limits. It's always good to do a physical check. At t going to 0, what do I have? E bar is equal to epsilon 1 plus e to the infinity, right? Well, it's e to the epsilon over 0, which is e to the infinity. So it's epsilon over 1 plus e to the infinity, which is 0. So that makes sense. The average energy, when the temperature is 0, the average energy is 0. And then what about if t goes to infinity? I have E bar is equal to epsilon over 1 plus e to the epsilon over infinity. So that's epsilon over 1 plus 1, which is epsilon over 2. So as t goes to infinity, the atom spends half the time in the upper state, half the time in the lower state, so its average energy is epsilon over 2. So there's an example of the two-state system. We worked out all the probabilities that the atom could be in any state, and we also worked out the average energy of the system using this formula here. Okay. So here is another way of visualizing the partition function. This is something I stole from the book by Schroeder, which is posted on D2L. What is plotted here is, his notation's a little different, so E of psi, that's the energy of some state psi, so E is on this lower axis here, and this axis here is the probability that the atom is in some state psi. And here are the states. You know, you've got psi 1 here, psi 2, psi 3, and each of those has an energy, and the energies are posted on that axis, right? And then this smooth line here is the line e to the minus e over kBt. So it's monotonically decreasing. It has a value equal to 1 here. And then it flattens, it falls off as energy gets higher. So each of these bars is the value e to the minus e over kBt at these particular energies. Okay. So if you want, you can think about the height of each one of these bars is kind of the value of the Boltzmann factor at that state. Maybe I should write that down. The height of each bar is the value of the Boltzmann factor e to the minus e over kt for that state. Maybe I should say for that energy, because energy is on on the y-axis, or on the x-axis, sorry. Okay, now this is at a particular temperature. If you change the temperature, the curve falls off at a different rate. So for example, if I had a higher temperature, it would look something like that. Oh, it's not very smooth. Let me try to do it a little better. Higher temperature would look something like this. Because at a higher temperature, you're more likely to be in some of the higher states because there's more thermal energy around to sort of use to get to the higher states. So the value of the temperature controls how quickly this thing falls off. If the temperature is very low, if I drew something really steep, something like that, that would be like a lower temperature. So high temperature, low temperature. Now, what is the partition function, z? It's the sum over all states of e to the minus ei over kBt. So basically what I would have to do is add up the heights of all of these bars over all of the possible states. So what you can imagine to calculate the partition function, one way to do it geometrically would be you would take each of these bars and stack them on top of each other. And then when you've added up the height of each of those, that gives you z. So this is the height of all bars when stacked on top of each other. So that's just one way to help visualize what's going on here.